All right, welcome everyone to next CPPC seminar. So today we have Anne-Katherine Burns from UC Irvine, and she's going to be telling us about Big Bang nucleosynthesis, and in particular a code that can compute the first minutes of the universe in seconds. So Anne-Katherine is a PhD student who's about to graduate and will be moving to Barcelona very soon. So I'm very excited to hear about all of this fancy code and to learn about the first few minutes of the universe. So thanks, Anne-Katherine, and I'll leave it in your hands.
Great. Thank you so much for inviting me for this invitation. I wish I could be with you all in Sydney, but maybe someday. So yes, today I'm going to tell you about PRyMordial, which is a code in Python that I have spent the last few years writing with my collaborators. It is finally publicly available, so we're very excited about that. And I'm looking forward to telling you all a bit about it today. Just so everyone's aware, unfortunately, I'm a little bit under the weather, so excuse me in advance if I'm coughing a little bit and having to take some breaks to drink my tea here, but hopefully it won't be too bad. Okay. So just an outline on what I'm going to be sharing with you all today. So I know not everyone here is an expert on early universe cosmology, so I'm going to start with a primer on early universe cosmology just to get us all on the same page. Then I'll be talking specifically about the physics of BBN, or Big Bang Nucleosynthesis. Next, I'll be introducing PRyMordial, our code. And then finally, I'll be briefly sharing about two different papers I've written with my collaborators using PRyMordial. The first is indications for a non-zero lepton asymmetry in the early universe. That one we published in PRL last year. And then the second is constraints on variation of the weak scale from Big Bang nucleosynthesis. That one we just put on the archive last week, so you all are the first to hear a talk on it. So this is very exciting. Of course, if there are any questions at all, please feel free to stop me. I would love for, even though this is a Zoom talk, for it to be somewhat collaborative. So I really welcome pauses for questions, comments, anything like that. All right. So as I assume you all probably know, our leading theory of early universe cosmology tells us that the instant the universe began, at the instant the universe began, it was infinitely hot and infinitely dense, and we believe it's been cooling and expanding ever since. I like this timeline from NASA. It's a little bit too reductive, but it does sort of kind of help situate the different events that we believe happened in early universe cosmology, and specifically situates where BBN is in relation to other events. So around 10 to the minus 32 seconds after the Big Bang, although this depends on your model, we believe the universe went through a period of rapid inflation. After this, at around 1 microsecond, we get the QCD phase transition, so the formation of neutrons and protons. At around 3 minutes, this is when Big Bang nucleosynthesis starts. So this is the creation of light nuclei like hydrogen, helium, lithium, etc. I'm going to be saying a whole lot more about that later. We get our first light, aka the CMB, at about 380,000 years after the Big Bang. At around 200 million years, we get our first stars. Around 400 million years, we get galaxies and dark matter. We crossed over into an era of dark energy domination around 10 billion years after the Big Bang. And then currently we are sitting at 13.8 billion years after the Big Bang, and we get things like Zoom seminars and people posting videos of their cats on the internet. Lots of exciting things happening at 13.8 billion years. Okay, so as cosmologists, one of our main goals is to understand the expansion history of the universe. And we do this by tracking 3 different components of energy density. These are radiation, matter, and dark energy. So taking a look at this plot on the left here, on the x-axis, we have density. On the y-axis, we have time since the Big Bang. So in the very early universe, this light blue region the universe was radiation dominated. What this means is that this blue curve representing our radiation density was on top of the other curves. We have more radiation density than we have matter or dark energy density. Big Bang nucleosynthesis happened during the radiation dominated era, so this is of particular interest to me and my collaborators. Right around the formation of the CMB, we get the matter radiation crossover point. This is the point at which matter began to dominate in the energy densities. As you can see, this red line is on the top. And then finally, fairly recently in cosmological history, around 10 billion years after the Big Bang, we entered a period of dark energy domination. So you can see right at the end of this thought, the green line surpasses the red and blue lines. There's potentially some interesting anthropic principle work to be done on why we have so, quote unquote, recently entered dark energy domination. That's not what my talk will be about, but that is potentially a little bit of a mystery. Okay. So technically, I am trained as a particle physicist. I will be graduating with my degree in particle physics. So why should I and other particle physicists care about the early universe? So as presumably all of you know, but I like to kind of remind people, the environments we can probe by studying the early universe are the same environments that we are creating in particle colliders. So really the phenomena that we're probing are the same, potentially, depending on the energy of our colliders, of course. But they're the same phenomena that we probe using early universe observables. In the early universe, at least, what I classify as the early universe, I'm talking about pre-CMB. So this is pre the emergence of the first photons that are allowed to reach our detector, before the universe was what we call transparent. So there are many potential observables that we can use to get a handle on this time period. Of course, there's Big Bang nucleosynthesis, there is the cosmic microwave background, there's baryonic acoustic oscillations, and lots more. I'm going to say a few words on these three, namely because they will also come up a little bit later in my talk. But there's many more ways to study the early universe as well that are very interesting. Oops. There we go. Okay, so I've been saying Big Bang nucleosynthesis, or BBN, a lot, but what actually is it? So I already hinted at this, but this is the production of light elements in the early universe. So again, we're thinking about the reduction of elements like helium, lithium, beryllium, etc. The purpose of studying it is twofold. The first is to determine the amount of radiation present at the time. Again, going back to that idea that early universe cosmologists want to get a handle on energy densities. And then the second is, of course, to determine the primordial abundances of these light elements. By studying these two things, we can put new constraints on new physics. And BBN is incredibly powerful, and it's often known as a parameter-free theory because every parameter in the standard model version of BBN has been measured. So it's extraordinarily powerful for constraining potential new physics ideas. All right, so next I'm just going to say a few words on the CMB. So the CMB is a background of low energy photons originating from the first combination of nuclei with electrons. Again, this is happening around 380,000 years after the Big Bang. For some reason, this event is called a recombination. I'm not sure why that is, because this is really the first combination. If you know, let me know. I feel like that would be a good thing for me to know as an early universe cosmologist. But we call it recombination for some reason. The purpose of studying it is to observe very small differences in temperature so that we can learn about the conditions of the early universe. I'm actually currently working on some CMB analysis, which I'm happy to talk about later if people are interested. All right, and then just a little bit on baryonic acoustic oscillations. So this is our third observable that allows us to get a handle on the physics of the early universe. Baryonic acoustic oscillations refer to alternating gravity and pressure, which created sound waves on the structure of matter in the early universe. These sound waves sort of imprinted as wrinkles on the structure of matter. So basically what was happening is that there were overdensities of matter which gravity pulled together. That matter then heated up, and because of that heat, there was then a pressure outwards, and a sort of accordion effect kind of happened that left this structure that we can now observe in large-scale structure data. The size of the oscillations is determined by the amount of normal matter, and dark energy. So yet again, this is a way for us to get a handle on those various energy densities that I was talking about earlier. All right, questions about anything I've said so far? Great. Okay. So now I'm going to dive a little bit more into the physics of BBN specifically. All right, so as previously mentioned, this is of course the production of light elements that we can think of as happening in sort of 3 stages. There are 3 important stages or periods of temperature that we can think of when we're thinking about BBN. The first is at temperatures below the QCD phase transition and above about 1 MeV. We have electrons, positrons, and photons and neutrinos existing in a plasma, and the photons and neutrinos were coupled together. And during this era, we get neutron to proton conversion happening freely and regularly. So neutron to proton conversion happens through a series of 3 reactions. These are neutron goes to proton plus electron plus antineutrino. Neutron plus neutrino goes to proton plus electron, and neutron plus positron goes to proton plus antineutrino. These 3 reactions are going to be important down the road for understanding what I'm saying a bit later. So please try to keep these in your head, and particularly notice the presence of neutrinos in these reactions. And specifically, they are electron neutrinos and antineutrinos. Our second temperature era happened around 1 MeV. So there were 2 important events that happened around 1 MeV. The first is that neutrinos decoupled non-instantaneously from the plasma. And the second is that the weak rates froze out. So the proton to neutron ratio gets set. Both of these events sort of allow nucleosynthesis to begin to occur, in particular, the weak rates freezing out. And then at temperatures less than 1 MeV, we're thinking about 3 minutes or so after the Big Bang, we get nucleosynthesis, which results in the primordial abundances of helium-4, deuterium, helium-3, lithium, and other elements. All right, so as you can see, I really like timelines and temperature lines, if you will. If the last slide was sort of the 101 version, this is the 201 version of our timeline. So this is same physics, just with a bit more added detail now that we're all kind of situated. So around 10 microseconds, we get the QCD phase transition. Thinking now in terms of time, just to help everyone sort of pair time and temperature together. Between 10 microseconds and 1 second, we get that neutron to proton conversion, again, happening through the series of 3 reactions. And then around 1 second or 1 MeV or so, we get the neutron to proton conversion freezing out at a ratio of 1 to 6 neutrons to protons. Now, the real purpose of this slide is to talk about this period, the period from about 1 second to 10 seconds. So this is the period in which we do think of as the beginning of BBN. However, an event happened that we call the deuterium bottleneck. The deuterium bottleneck essentially refers to the fact that at this time, of course, the photons were still very hot, and the average photon energy was above the deuterium binding energy. So the first reaction of Big Bang nucleosynthesis that created deuterium was proton plus neutron goes to deuterium plus a photon. So basically, proton and neutron would come together, produce deuterium plus a photon. But as soon as that deuterium is produced, a high energy photon would hit it and break it apart. So deuterium was not stable at this time. During this time, for about these 9 seconds or so, neutrons were decaying via beta decay. So the neutron to proton ratio was continuing to decrease to a final value of about 1 to 7, which is really important when we do the calculation of our light elements. At around 10 seconds, deuterium became stable and BBN is allowed to proceed. So the other reactions are allowed to happen that involve deuterium. The one other important note here is that the majority of the neutrons that get produced or that result in the neutron to proton conversion end up in helium-4. And this is another fact that's going to come back. So remember the neutrinos participating in the weak rates, and remember that most of the neutrons are ending up in helium-4. Okay, so this is a schematic diagram showing the 12 most important thermonuclear reactions that happened during BBN. Obviously, it's very complicated. I actually tried to make this plot with 63 reactions, and it was just way too much to look at. So we're going to stick with the simplified version. It is possible to study up to more than 400 thermonuclear reactions. However, the reason that I've labeled these as, yes, is there a question? Is that a question? No,
are you saying
just chatter.
Like, your thesis have a mode where it's as number of
Okay, I'm going to assume this is just chatter going on and keep going here.
Well, it's not really.
But please let me know if there's a question. Okay, great. So these are our 12 most essential nuclear reactions. And they are labeled as such because if you do the calculation only with these 12 reactions, you're going to get very close to the most theoretically precise values. If you add in more reactions, which our code does allow you to do, you will get more precise values, but there's kind of diminishing returns in this way. So these 12 reactions will really allow you to compute the abundances of the primordial elements quite both efficiently because you're doing fewer calculations with fewer reactions and accurately. Okay, so every time I give this talk, people are always curious to know how these light elements are observed. So I should give a disclaimer on this slide to say that I am not an observational astrophysicist. However, I do want to share some of the work of observational astrophysicists just so I can answer that question in advance before it's asked. So thinking about our three most important observables for BBN. Starting with helium-4. So helium-4 was produced at about 24.7% during BBN. And helium-4 is observed in what we call metal-poor galaxies. So this is the astrophysicist version of metal, aka metal core, meaning anything heavier than helium. So these are young galaxies that are primarily composed of hydrogen and helium. So in these galaxies, primordial interstellar gas is ionized by photons that are emitted from young stars. And then the gas cools in a number of strong emission lines. And by observing those emission lines, we can get a handle on exactly how much helium-4 exists in those young galaxies. And then we can extrapolate to get our observational value for the primordial abundance of helium-4. The observable value for the primordial abundance of deuterium is measured in a somewhat similar way, also using spectroscopy. In this case, deuterium is observed as a weak absorption doublet of hydrogen. And this is done by observing hydrogen in distant gas clouds that are backlit by quasi-stellar objects. Again, we're looking to probe here very low metallicity environments, so environments that are have very low amounts of anything heavier than helium. Finally, we have lithium-7. So lithium-7 was produced at about 10 to the minus 10%, so just a very tiny little bit. But of course, we still care about it because the entire calculation of BBN is so precise. Lithium-7 is observed in stellar atmospheres, and it is very difficult to get a truly accurate observation of lithium-7. So there's large error bars on the observational value. And for a long time in the world of BBN, there has been this thing known as the lithium problem. For a lot of people that know very little about BBN, they'll know that like there's some kind of problem with the lithium. Happily, hopefully, this problem has hopefully been solved by Brian Fields and his collaborators at the University of Chicago. They have proposed that, long story short, we don't understand the stars. Stars are extremely complicated objects. In particular, the conduction that happens in stars due to currents of heat within the star can drag lithium down into the core of the star and potentially push lithium up into the core of the star. So the fact that our theoretical value that we get for lithium-7 when we do our BBN calculation and the observed value are in tension with each other can hopefully be solved by this. However, there are some potential other solutions proposed also, all relating to needing to tweak our observational value and nothing to do with the theoretical value. All right, any questions about any of that?
So I guess these observational probes, you're assuming that there's negligible amounts of non-primordial helium, deuterium, and lithium. Is that correct, or do they sort of?
That's right. Yeah, in these young galaxies, you assume there's negligible amounts. That's exactly right.
But you would get like, do you get some lithium from like cosmic rays bombarding stuff?
Sure, and this is another reason that the lithium is difficult to measure. Yeah, the lithium measurement is particularly difficult, and that's one of the reasons that there are large error bars on it. You're right. However, we do still assume that the majority of it that we're observing is primordial.
Thanks.
Anything else? All right. So now I am going to talk about our code PRyMordial. So PRyMordial is a code that is written in Python, the purpose of which is to simulate the evolution of light nuclei production in the first few minutes after the Big Bang. We calculate n effective, which parameterizes the number of light degrees of freedom in the early universe, as well as the abundances of helium-4, deuterium, helium-3, tritium, and lithium-7. We include many corrections to the sort of, simplified kind of textbook version of BBN. These include QED plasma effects, correction to the neutron lifetime, and incomplete neutrino decoupling. So why did I spend the majority of my PhD working on this code and these projects? So there are several other publicly available BBN codes out there. However, all of them had shortcomings that we wanted to create a code that could sort of resolve. So one of the most famous is called Parthenope. This is an excellent code. It's written in Fortran, so it's a bit outdated at this point and not particularly accessible for young researchers. And the thermonuclear reactions that they use are not up to date anymore because it's a rather old code. The other fairly famous one is PRyMat. This is also an excellent code that I have used plenty as I was working on our code PRyMordial. However, this code is written in Mathematica, so it's quite slow and it's difficult to modify. So we kind of had two overarching goals when we were creating PRyMordial. The first was to write a code in Python that would be fast, efficient, and easy to use for younger community members, especially. And the second was to create a code that would be really easy to add in new physics. BBN can be really daunting just because there is so much that goes into it. So we really wanted to make it accessible and a little bit less daunting for people who are not used to thinking about BBN. It has plenty of other advantages as well. I'm not going to read all of these on the screen right now, but I will point out this last bullet point, which is that within the code, we also have an option to use Julia, which is a coding language developed by some people at MIT that enhances our efficiency, so makes the code run faster. All right, this is a diagram kind of showing the structure of the code and kind of the nuts and bolts of how it works. So the code is written in several modules. Our main module basically is just sort of the brain of the code. It takes in information for all the other modules and does our final computation of the light elements. We also have an initialization code. In this initialization code, there are a whole bunch of true or false flags that make it really easy to explore a variety of parameters within the code. You can, for instance, turn on a new light species that coupled to the neutrino just by switching a flag from true to false. You can change which set of thermonuclear reactions we're doing. In my next slide, I'm going to come back to that comment. And a whole bunch more. So there's some fun things to play around with in that initialization code. We also have our thermodynamics code. So this computes the BBN plasma rates, including corrections from the code NUDEC VSM. If you're familiar with this work, you might know that code. We have a module which computes our weak rates, our neutron to proton conversion rates. And then there's an option within this module to speed up the calculation by telling the code to not recompute the rate. So once you run the code for the first time on your machine, the code will store the results of the computation of the proton to neutron reaction rates. So you won't have to do that piece of the calculation each time, which speeds things up. And then finally, we have our nuclear network. So this basically sets up the system of differential equations that allows us to compute our final abundances for the light elements. In my backup slides, I have a whole bunch more information on the really nitty-gritty of the code. I am happy to share my slides. Unless people ask, I won't be going over that in great detail. This is sort of my slide for the nuts and bolts. But if anybody has more questions about the specifics of the computation, I'm happy to answer them. Okay. So I said that I would come back to this note in my next slide. So this is just a quick aside about the thermonuclear reaction rates. So this up here is this scary set of coupled differential equations that we use to solve for our final abundances. The abundances are these Y values. So as you can see, this is a differential equation in time of our abundances of each species. The reason that I put this equation up here is to point out the presence of this gamma. So this gamma represents our thermonuclear reaction rates for each reaction that plays a part in the final abundance of each species. So for instance, for helium-4, we would have to include every reaction in our list of reactions that has helium-4 in it. These thermonuclear reaction rates are not known from first principles, so we have to get them from data. And we have two different approaches when it comes to getting them from data. We get them from two different sources. The first is what we call our PRyMat-driven source. These nuclear rates are implemented according to the statistical determination of various groups. So we basically pull data from a bunch of groups. These are the same thermonuclear reactions as the PRyMat code uses. So if you're familiar with that code, these are the same reactions that they use. You can also choose in the code to use what we call the NACRI-2-driven reactions. These are nuclear rates that were compiled by the NACRI collaboration in 2013. Now, because 2013 was 11 years ago, which is crazy, we also include in this set of reactions two updated reactions, so two reactions that we have newer data for. And these are deuterium plus proton goes to a photon plus helium-3, and beryllium-7 plus neutron goes to a proton plus lithium-7. So again, in that initialization piece of the code, you have the choice whether or not you want to use the PRyMat-driven reactions or the NACRI-driven reactions. And it's as simple as flipping a switch from true to false. Depending on which you choose, the results do change of the final abundances, and I'm going to show that in one of the examples that I'll talk about shortly. Okay, So what are the results of PRyMordial? So there's a ton that you can do with this code, of course. I just wanted to show this famous PDG plot. So you probably have seen a plot very similar to this that the PDG has in their VBN section. So we can reproduce this using the code here in this white box. We, a few months ago, put out a paper that's sort of a manual on PRyMordial. And in that paper, we do have this specific code. So if you'd like to produce this plot, you can just copy and paste that code from our paper. So just to kind of walk through what this plot is showing, on the x-axis here, we have the baryon to photon ratio, which is being varied to get a variety of different element abundances. These dotted lines are our theoretical abundances that come from PRyMordial. These are the results of PRyMordial. So we have the theoretical abundance of helium-4 in green, the theoretical abundance of deuterium, helium-3, and lithium-7 on the bottom. Excuse me. So looking at this top box here, because it's the nicest. So this yellow box is showing our 1 sigma error bars on our observed value of helium-4. So as you can see, this is sitting right around 24 to 25% or so is our 1 sigma error bar on helium-4 for the observed value. And then this light blue line here is showing the CMB constraint on the baryon to photon ratio. So from the CMB, we can determine what the baryon to photon ratio should be. And as you can see on our helium-4 panel up here, we get perfect overlap between our theoretical value, our light blue line for the baryon to photon ratio from the CMB, and our constraints from observation. So that's great. BBN works, or excuse me, helium-4, our helium-4 calculation works perfectly. As you can see here, hopefully we have a tiny, tiny yellow box for the deuterium. The error bars in this case are very, very tiny. But also for the deuterium, we get overlap between our theoretical value, our eta baryon value, and our experimental value for deuterium. And then finally, on this bottom panel, this is sort of showing what the lithium problem is. So these are using the old error bars for the observed value of lithium-7. And as you can see, we do not get overlap between the yellow box, the purple line, and the blue line. So here, this is sort of showing that our experimental observational value for lithium-7 does not correspond to the theoretical value for lithium-7 when we use the CMB value for eta baryon.
Sorry,
Okay.
can I ask about the lithium? Does that bar, is the lithium abundance consistent with 0, or is it just is the error bar just below 10 to the minus 10?
Sorry, trying to go back to this plot here. There we go. It is not consistent with 0. No. Yeah, it's just below 10 to the minus 10.
Yeah. Okay. Thanks.
Yeah. Thanks for the clarification. Mm-hmm. Any other questions before I move on? Okay. So I mentioned before that one of our main goals when we were designing PRyMordial was to make it really easy to add in exciting new physics. So some of the new physics that would be easy to add into the code are new light degrees of freedom. You could change your interaction strengths at relay times. You could potentially change your standard model Yukawa interactions, and so much more. The universe is your oyster. I think this code is really fun to play around with, and hopefully easy to play around with. I actually used it with a group of high school students 2 summers ago. They were looking at the effect of varying the neutron lifetime on the light element abundances, and they wrote a fun little research paper. Point being, so this code is accessible for anyone from high school students all the way up to the professor level, and it's easy to play around with. So we hope you'll give it a try. That's my advertisement. All right, questions about this piece? All right. If not, I'm going to move on to my examples. Starting with indications for
sorry.
a non. Yes,
Sorry.
of course, no problem.
Yeah, I was just wondering. So maybe you won't come back to this, but you were talking about the different methods of getting the nuclear rates, and presumably that entails like a theoretical uncertainty on those lines that you were just showing. Do you know, like, if you were to add that to the plot, do you know how like thick that error bar on those lines would be? Is it sort of noticeable, or is this something which is quite well pinned down now?
No, it's a great question. So we didn't include it just because it made the plot look messy. But for helium-4, the theoretical error is really negligible. It's more than an order of magnitude smaller than the observational error bar. For deuterium, the theoretical error bar is comparable to the observational error bar, which, as you can see, is really tiny. Off the top of my head, I don't remember about the lithium, but yeah, it's not larger than the theoretical, or excuse me, than the experimental error bar.
Okay, cool, thanks.
All right. So moving on to talk about indications for a non-zero lepton asymmetry. All right, so I've been talking big talk about what a great theory BBN is. However, as of, I believe their paper came out in 2021, we have some new data on the helium-4 abundance. And there's potentially a 3 sigma tension between this new observed value and the standard model. So the Subaru survey observed 10 extremely metal poor galaxies and combined this new data with pre-existing data to get a new observed value for helium-4. The observed value that they got is the top line here in this blue box at the bottom of this the slide. They found 0.2379, and just by eye you can see that there's something wrong here with the difference in the first line and the last line in this box, which is our theoretical value. So as I mentioned, there's potentially a new 3 sigma tension with the standard model. And our goal in this paper was to see if we could resolve this tension by introducing a lepton asymmetry, which I will get to momentarily. There's also potentially an anomaly in the deuterium. This one is a bit contentious. So the current observed value has a 2 sigma tension with the theoretical standard model value. However, as I mentioned, one of the really tricky pieces of BBN is understanding the thermonuclear reaction rates. And there have been arguments that maybe we just don't understand those thermonuclear reaction rates well enough, in particular the error bars on them. So whether or not you believe this 2 sigma tension, depends on which side you take of that argument. However, we decided to take both of these tensions seriously and see if we could come up with a theory model to resolve them. Okay. So as I mentioned, we wanted to introduce a primordial lepton asymmetry into our calculation. So this lepton asymmetry, A to L, is equal to 1 over the number of photons times the sum of the number of neutrinos minus the number of antineutrinos. And this lepton asymmetry can be parameterized using these degeneracy parameters for each flavor. So you see for our 3 flavors is equal to the chemical potential of each neutrino flavor divided by the temperature of each flavor. This lepton asymmetry affects our calculation of our light element abundances in 2 different important ways. The first way is that it affects our radiation density. So as I mentioned, one of the important parameters that we are calculating in our code is delta N effective, or N effective, which parameterizes the number of light degrees of freedom in the early universe. And as you can see by this formula at the bottom of the screen, our degeneracy parameter for each neutrino flavor plays into our radiation density. So before we even think about BBN at all, we can already put a constraint on these degeneracy parameters from CMB data. So the Planck corroboration has a constraint on ineffective. And from that constraint on ineffective, we can put a bound on what the sum of our degeneracy parameters for each of the flavors should be, all squared, or for each individual flavor. We can also put a constraint. So each individual flavor, the degeneracy parameter must be less than 0.71. This is a little bit more stringent for the second and third generation neutrinos, which I'm going to talk about in just a minute here. Okay, so that was kind of the first way that we can think that our degeneracy parameter will affect the physics of BBN. The second is that specifically the electron-neutrino asymmetry will change the way that the weak rates work, as well as neutron decay. So if you remember a whole bunch of slides ago, I was talking about proton to neutron conversion and the participation of the electron neutrino in those three rates. And here we can see exactly how the degeneracy parameter of the electron neutrino affects the neutron to proton ratio. So our neutron to proton ratio is equal to the exponential of the proton neutron mass difference divided by the photon temperature minus the degeneracy parameter for the electron neutrino. So once we introduce an asymmetry, specifically in the electron neutrino sector, we're altering our proton to neutron ratio. And by altering this proton to neutron ratio, we're especially changing our final helium-4 abundance, which is because the majority of the neutrons end up in helium-4. So helium-4 is especially sensitive to the neutron to proton ratio. All right, so these are our results of that analysis. There's kind of a lot going on this slide, on this plot, so I'm going to take my time and kind of walk you all through it. So on our x-axis here, we have delta N effective, which of course is our change in N effective. And on the y-axis, we have our degeneracy parameter. This is specifically for the electron neutrino. In our vanilla lambda QCD model, of course, we have zero change, excuse me, in delta N effective, and we have zero degeneracy for the electron neutrino. Our blue and red ellipses here correspond to our 1 and 2 sigma results using those two different sets of thermonuclear reaction rates. So the blue corresponds to the results that we get using the Priemat-driven rates, and the red corresponds to the results that we get using the Nacre-driven rates. So like I mentioned before, you do get a difference. Notice here that within 1 sigma, both the Priemat and the Nacre-driven results are compatible with a delta N effective of 0. So you don't need to adjust your delta N effective at all to get the correct values for helium-4 that we're looking for to match the observation. However, you do need a small shift in your degeneracy parameter for the electron neutrino. So really the takeaway from this plot is that having a non-zero electron asymmetry can potentially resolve our tension here. Just to kind of drive this point home, these are our probability distribution functions for our helium-4 and deuterium abundances. So again, kind of a lot going on these plots. I'm going to focus on this left one here because it's a little bit easier to kind of see what's going on. So starting with our two colored bands here. So the light green band corresponds to our 1 sigma error bars for the previously accepted observed value of helium-4. That's the PDG 2021. And then this dark green band corresponds to that new Subaru value, the 1 sigma band for the new Subaru value. These dotted lines here are our standard model predicted value, theoretically predicted value, which you can see sit right within the light green band. So that's good. Without changing anything in the standard model, we are compatible with the previously accepted observed value for helium-4. And then the shaded in regions here correspond to our new theoretical values for helium-4. As you can see, these distributions are peaking inside the dark green band, so that's good. Bayesian analysis works, and this is exactly what we wanted to do. So using that shifted degeneracy parameter for the electron neutrino, we can get probability distribution functions for our helium-4 that are peaking within this dark green band, which again corresponds to that new value. Okay, so we find a degeneracy parameter of somewhere between 0.01 and 0.26 will resolve our helium-4 tension. This value is, of course, much, much larger than our baryon asymmetry. And we thought just a little bit about what type of new physics could generate this asymmetry that's much larger than the baryon asymmetry. So at temperatures above the electroweak breaking scale, electroweak scalarons will equilibrate the V plus L symmetry. So we basically had to figure out a way to allow for a lepton asymmetry that was so much greater. So for that much greater lepton asymmetry to exist, we sort of thought about two different scenarios. One is the kind of more vanilla one. The asymmetry could be generated after the scalarons become inactive. So at temperatures at or below about 100 GeV. Or the potentially more interesting option is that maybe there's some flavor dependence in the new physics sector. So perhaps the total lepton asymmetry is much less than the individual lepton asymmetries. Again, what we were constraining here was the degeneracy in the electron neutrino. So perhaps there could be individual flavor asymmetries that are a lot greater than the total lepton asymmetry. All right, so takeaways from this paper, our analysis of the primordial helium abundance using the Subaru survey data hints towards potentially a large total lepton asymmetry originating in the early universe. We used both BBN and CMB data to get this result to derive our constraints. And this large lepton asymmetry could be an important clue towards understanding the early universe. All right, questions about any of that? I know I've been throwing a lot of information at you all. All right, if not, I'll keep going with my last little piece of the talk here. And this is on constraints on variation of the weak scale for Big Bang Nucleosynthesis. Again, we just put this paper on the archive this week. So if you're interested, please check it out. This was a paper that we wrote basically trying another tactic for resolving the same helium anomaly that I've been talking about. So just to remind you, the Subaru survey found a value of 0.2379 for our helium abundance, while our standard model theoretical value is 0.247. The way that we tried to resolve this anomaly in this paper was to vary the Higgs vev. The Higgs vev is, of course, the only dimensionful parameter in the standard model. And we thought about, of course, how varying the Higgs vev would affect BBN. We already know that the vev is cosmologically dynamical. It must have varied during the electroweak phase transition. So we thought we could potentially come up with a reasonable scenario in which the value of the Higgs vev might be different during the time period of BBN than it is today. Okay, so I know this slide is a little bit messy, but let me kind of walk you through it. So these are the effects of varying the Higgs vev on BBN. The first effect is that varying the Higgs vev changes our weak rates. So it does this, of course, because our quark and electron masses change when we change the Higgs vev, and also our proton to neutron mass difference changes when we change the Higgs vev, both of which are important, all of which are important parameters when we calculate our weak rates. Varying the Higgs vev also changes our deuterium binding energy. So if you remember when I was talking about the deuterium bottleneck, calculating the deuterium binding energy accurately is an important piece of solving for our final primordial abundances. In the deuterium binding energy, the parameters that we looked at that changed based on the varied Higgs Bev were the pion mass and the sigma and omega meson masses. All of these go into a calculation for the deuterium binding energy that essentially just amounts to solving the Schrodinger equation. And then finally, the Higgs Bev, varying the Higgs Bev also affects the thermonuclear reaction rates. So in our paper, we showed that the thermonuclear reaction rates go like lambda QCD, and we found that lambda QCD varies like the Higgs Bev to the power 1/4. So our new thermonuclear reaction rates are equal to our old thermonuclear reaction rates times 1 plus delta V over V to the power 0.25. All right, so here are our results for the effect on the weak rates and the deuterium binding energy by varying our Higgs Bev. Starting over on this left side here, so our top panel is for the change in the rates for the neutron to proton. Neutrons go to protons, and the bottom panel is for protons going to neutrons. Here, we're looking at varied temperature for dV over V equal to 0.01, or positive plus or minus 0.01. So our dotted line here corresponds to negative, a dV over D equal to negative 0.01, and our solid line corresponds to a dV over D equaling positive 0.01. For a deuterium binding energy calculation, this plot is slightly different. So we're showing the deuterium binding energy for varied values of dV over V. As you can see, this red dotted line here shows our theoretical value for dV over D equals 0, which is 2.22 MeV. And then depending on whether you let your dV over D be positive or negative, you get varying deuterium binding energy that either goes increases or decreases. These are our results for the effect of varying the Higgs Bev on the helium-4 abundance. So again, just walking you through this plot. This is similar to our deuterium binding energy plot in that we have our varying plus or minus dV over V on our x-axis and then our helium abundance on our y-axis. The experimental value from the PDG, so the previously accepted experimental value is this coral band here. The gold band is the experimental value from the Subaru survey. The Empress collaboration is the collaboration that published those results, so that's why this label is Empress. Again, our red dotted line is our theoretical value for dV over V equals 0. And then, as you can see, our blue and green lines are what happens to our helium abundance when you allow dV over V to vary in either positive or negative direction. So from this plot, if you believe the PDG experimental value, then we can get two sigma bounds on dV over V. Our bounds are that dV over V must be from minus 0.01 to 0.004. And if you believe the Subaru survey data from the Empress collaboration, then our two sigma bounds on dV over V are minus 0.03 to minus 0.01. And note that dV equaling 0, so having no change in the Higgs Bev, is mildly excluded for the Subaru survey results. So that's kind of interesting. All right, so this is a very similar plot for the deuterium abundance. Again, we have our varying Higgs Bev on the x-axis. We have our deuterium abundance on the y-axis. This coral band is our experimental value for the deuterium. And then again, our blue line here corresponds to the change in our deuterium abundance for positive values of dV over V. And the green line corresponds to the change in deuterium for negative values of dV over V. Our theoretical uncertainty, it should be noted here. I said this a little bit earlier, so thanks for the question about that. Our theoretical uncertainty for the deuterium is comparable to the experimental uncertainty. Because that, our bounds on dV over V go from minus 0.001 to 0.06. And if you notice, these two sets of bounds that we get from the helium versus the deuterium are not compatible with each other. So essentially the results of our paper are that we can solve one anomaly or the other, but we can't use the same change in the Web to resolve both at the same time. So that's too bad, but science is science, and this paper still potentially points to an interesting model and an interesting way to solve at least one of these anomalies. All right, so takeaways from this paper. So the analysis of the helium abundance from the Subaru survey data potentially hints in variation in the Higgs Bev between the BBN era and today. However, like I just mentioned, there is no value of varying Higgs Bev that can explain both the Subaru and deuterium anomalies, but we can certainly explain one or the other at a time. And then we can imagine an extended model in which the Higgs Bev slow rolls to its current value, but maybe hasn't quite reached it at the MeV temperature scale. We didn't really think further than this, but there's potentially some interesting physics to do there on what exactly that model could look like. All right, and that's all I have for you. Looks like it's 5:01, so I think I did pretty well on my time. Thank you so much for listening. If there are other questions, I would be really happy to take them. And thank you again for the invitation to give this talk.
Thank you. Thank you very much. Yeah, I think we have some time for questions. Tony, did you want to go first?
You're talking to me?
Yeah.
Oh, good. I hadn't even put my hand up. Yeah, so I had a couple of questions. Back at the beginning, you were showing temperature versus time. Can you remind, is there some simple formula for how the temperature varies with time? It's some power, I guess, right?
Yeah, it's not so simple. We do compute it in the code. Time is a function of temperature and temperature is a function of time. The thing that I usually remember is 1 MeV corresponds to about 1 second, and that kind of anchors me.
Okay. You didn't talk about density. So what's the density of the universe at that time at 1 second, at 3 minutes?
I couldn't tell you off the top of my head. We
because the universe
would be thinking about
pretty small
radiation
at that time, right?
Pretty small, but I don't know the exact value.
It'd be great to also show that. How accurately do you claim to know the entropy ratio in your standard model?
It's quite accurate. As I showed with the degeneracy parameter example, there's a variety of potential new physics models you could add in that would change the entropy ratio. However, in the standard model, our theoretical error bars are quite small on our neutron to proton conversion rates.
So is that 1%? Is it 10%, 0.5%?
I think about 1%.
Thank you.
Yeah, for sure. Thank you.
Mikhail?
I just had one question about the VEF variation there in the end. So the Fermi constant should also vary, right? So if I look at the interaction rates, so weak interactions like neutron decay, there it goes like G Fermi squared, so which is 1 over VEF to the 4th. So did you include those variations? So you talk about masses and then the QCD strong coupling.
So it's funny that you asked. This is actually a contentious topic. Within our collaboration, I was arguing for including corrections to the Fermi constant as well as several other constants. In the end, we decided to keep things a little bit simpler and only vary our quark and electron masses and lambda QCD. Because those are sort of the main pieces that are going to have significant effect on BBN. However, you're exactly right. The Fermi constant will indeed vary. So depending on who you talk to, it may or may not be important to include that.
Good, thanks.
Yeah, maybe I can also ask about so you mentioned this, the two anomalies seem to want to pull you in different directions for this delta V. If you're imagining some scenario where the Higgs is like rolling down, could you engineer some oscillations which would make it positive at one time and then negative another time, and they could balance in a certain way to reproduce both of them, or is that getting a little bit too fine-tuned at that stage?
No, I mean, it's a good question. Like, I think you could certainly imagine a model that did that, you know, somehow having an oscillating VEV. And, you know, it wouldn't need to oscillate too much. We're talking about changes, you know, very, very small changes. That would, you know, be quite a fine-tuned model, but, you know, who's to say that's not the way that the universe worked? Of course, it would be extremely specific, and you would have to make sure that you're not messing up any other early universe observables if you do have an oscillating VEV in that way.
But it is this I mean, this variation in the VEV in general, is this motivated by some other BSM framework or something? Is this something that people have suggested prior to this study, or which you're sort of treating phenomenologically?
Yeah, so there was actually there was a paper that came out quite recently on the archive, just within the last few days. I haven't had time to read it carefully, but I really want to. And they suggest a model in which the Higgs VEV varies in the early universe. If you're interested, after, I can point you towards that paper.
Yeah. So is anyone else? Please just unmute, but see anyone. Okay, so I think we exhausted all the questions. So yeah, thank you again very much for giving a nice seminar. And yeah, I guess we can finish there. So I might chase you up for your slides afterwards, but
Oh, for sure.